Good afternoon and welcome to Hand-Wavy Chemistry, where we do not delight in the details, but rather bask in the big picture. Today, I would like to talk to you about acids. There are three main definitions for acids. The first and simplest is the Arrhenius acid. An Arrhenius acid is a compound that when it is placed in water, it dissociates, releasing protons, which go on to form hydronium ions. You'll often see chemists just write H+. What they actually mean is H3O+, as protons cannot just simply float around freely in water. A simple example of an Arrhenius acid is something like HCl, hydrochloric acid. Click the link up here to see why that may or may not be the best name for that acid. When hydrochloric acid is in contact with water, the proton, the H+, that is attached to the chloride, is transferred to a water molecule. Now we have Cl- and H3O+. And it is this concentration of H3O+ that we are reporting on whenever we give the pH of a solution. You'll often hear people talk about strong acids and weak acids. In the case of our Arrhenius acids, what that is describing is the degree of dissociation. A strong acid, like HCl or nitric acid, fully dissociates. When you put them in water, they lose all of their protons. A weak acid, on the other hand, like acetic acid, which is also vinegar, that one only partially dissociates. Only some of the protons come off. So in solution, you would have some protonated acetic acid, some deprotonated acetic acid, and the hydronium ions that were formed when that deprotonation occurred. A limitation of these Arrhenius acids is that they must be in aqueous solution. They must be in water. So another way to think of acids is the Bronsted-Lowry acid, where we think about that proton and we say the acid is a proton donor. We saw before the HCl, the proton was donated to a water molecule, making the hydronium H3O+. We could also do this with something like hydrochloric acid, HCl, and NH3, ammonia. The proton could be donated from the HCl to the NH3, and we end up with a Cl- and an NH4+. We end up with ammonium chloride. The final type of acid is called a Lewis acid. And in this, we think not so much about the proton that's moving, but rather the lone pair of electrons that are accepting it. So we flip the script. It's no longer proton donors, it's electron acceptors. The HCl reacting with the water, there are lone pairs on the oxygen. So the proton is accepting a lone pair from the oxygen. When it was HCl and NH3, the proton was accepting the lone pair from the nitrogen. One advantage of thinking about acids in terms of electron acceptors is that it dovetails nicely with redox, reduction oxidation chemistry. In redox chemistry, electrons are transferred or given and accepted, and the oxidation state or the charge of the atoms changes. In the case of Lewis acids, the electrons are shared, they are donated and accepted. However, the formal charge on the individual atoms does not change. So now we can start to have acid-base systems that don't even involve hydrogen anymore. We can start to have metals acting as Lewis acids. So if we have a transition metal like iron dissolved in solution, and water molecules begin to come and they coordinate to it, the iron is acting as a Lewis acid. In the case of some boron species, where we only have 3 bonds, there are vacant orbitals above and below the boron that a lone pair of electrons could come in and interact with. So these BX3 species are Lewis acids. An example of an acid-base reaction that involves no protons is the adduct formed when boron trifluoride reacts with ammonia. The lone pair on the nitrogen is accepted by the boron, and we have an acid-base reaction occurring. That is, at least, according to the Lewis acid theory. It is important to understand that all of the Arrhenius acids are also Bronsted-Lowry acids, and all of the Bronsted-Lowry acids are also Lewis acids. And the thought process and terminology you should use depends on the application. Acid-base reactions are not just simple one-direction affairs. In fact, they tend to involve dynamic equilibria, with species able to transfer back and forth as protons or electrons are shared differently, with the amounts of each species present depending on the relative strengths of the various acids. But that is a story for another day. I hope you have enjoyed this video, and if you have, please make sure to like and subscribe and share it with your friends. And if there is anything you would like to contribute to today's discussion, or a topic you'd like to see covered in a future video, please put it in the comment section below. Thank you, and I hope you have a wonderful rest of your day.